Hi, so today I'd like to talk about what's going on when your MacBook does not see the battery, when your MacBook will not run off the battery, when it does see the battery but won't charge, or does see it won't run off of it, and the differences between all these different problems. There is a lot of misconception going on here, and a lot of people have this concept dead fucking wrong and don't have a basic understanding of how the system works, which is why I feel the need to do this video. And I was reminded of this when I just got an email from an ex-client the other day asking about, the fuse that blows when it won't see the battery. Because, yeah, of course, it's just like a magical fuse. It's not like there's a system running inside of here with many different data communication lines and detections and other things. No, it's just a fuse. And that's what the guy asked. So to give a little backstory on this one particular jackass, it's somebody who sent in a bunch of machines a while ago and a bunch of boards only. And as many of you work in the business know, board-only clients are the worst. They will drive you nuts. And this person sent something in. We fix it. We send it back. This guy gives my staff a good 20-minute lecture on how we suck at everything we do. And we apologize, and we say, send it back, but this time send the whole machine so we can see what's wrong with it. It was the RAM. Like, his RAM was causing it to beep. And we weren't jackasses about it. I didn't rub it in his face the way you would imagine, because, again, in my professional life, when I get on the professional phone in the real world, I am me, but I'm the type of me that I would give money to, even if, I was an idiot and I did something stupid. I try to keep it, civil. And in spite of that, he just fell all over himself. I'm pretty sure he murdered some of his staff members after this because of the lecture that he gave based on what they told him. But anyway, I just get this email the other day, and every now and then I get email asking for advice from this one guy because he just lacks the gall to ever send something to me again or give me money again, out of fear that I'll probably just beat the living shit out of him if he pulls that crap again. But he sends me an email and it's asking, what do you do? What fuse do I replace? Which, again, just the fact that experienced repair centers are asking me what fuse blows when the battery stops working just means that there's a fundamental lack of understanding about how the system works, and that's what I'd like to discuss with this video. So I got the screen capture going on here. One of the things I hate about the screen capture is that for some reason it doesn't want to see the damn mouse. It is better than me using a pointer and the quality you get with the camcorder going on the TV. But anyway, you're just going to have to listen to me and where I tell you to look on the screen when I'm trying to draw your attention to something. So here we're going to start with an A1278 from 2012. This is an 820-3115 board, and we're going to start with the battery connector. So right over here, where it says, here we go, battery connector. Hopefully you can see what I'm selecting. It says a J6950. So let's see. So over here we have actual power. We have a bunch of ground tabs. We have SysDetect L, SMBus BAT SCL, and SMBus BAT SDA. So the important thing here is obviously power is coming from the battery, so that's going to be on PPV BAT underscore G3 hot underscore con. Then there's communication with the battery. How does the system know the battery is connected? How does the system know the percentage left in the battery? How does the system know how many cycles are on the battery? All of this communication is done with something called the System Management Controller, or the SMC. You've probably heard of the SMC in terms of when something is going wonky or fucked up, you do an SMC reset and things work nicely again. The SMC controls all of this. It tells the system to turn on. It tells the system to charge the battery, stop charging the battery, run off the charger, don't run off the charger, all of that good stuff. And you have these two lines here, SM bus. Anything that says SM bus is going to be communication with the SMC, and SM bus BAT SCL. So let's see where these things go, what they do, and I'm also going to go into some basic concepts here, such as what is a pull-up resistor, what is a current sensing circuit. So there's going to be a lot of concepts merged into this one video, and they're all concepts that you should read up on your own if you are a little behind in terms of understanding how these types of electronics work. So if you'd like to look up what is a pull-up resistor, take the time to do that now. Pause the video. If you want to look up what a current sensing circuit is, look up what a current sensing circuit is. Do that now. Pause the video and then come back to this. Now, what I'm going to do here is I'm going to show you what a pull-up resistor is and how it works, at the very least, in this basic little circuit here. So this probably looks like a bunch of confusing shit to you, and you have no idea what the fuck is going on. And I assure you, you have no reason to feel bad, because there was once a time when I looked at this and I had no goddamn idea what was going on. So let me show you how this basic thing works. You see over here where it says SMC, of course you can't tell that I'm pointing, but what the hell, I'm used to it. Right here in the upper right corner where it says SMC5 SM bus connections, where I'm selecting over here, see this, where you have R5280 and R5281 everyone. Let me show you what this is. So you have PP3V42_G3 hot. If you've seen my other videos, you understand that these are just basic voltage rails. Don't be scared by all that crap. PP3V42 just means that that's where 3.42 volts is. That is a power line on the system. The system has a 12-volt power line called PP bus G3 hot. It has a 5-volt power line called PP5ES5. You have PP3V42, which is a 3.42 volt power line. So that's the 3.42 volt power line of the system. Now what this is this is a communication line. So this is where the SMC is talking to the battery charger chip, which is the U7000. The U7000 creates the 12 volt rail for the computer and also creates the 12 volts that charges the battery and the actual battery itself. So this is communication between the SMC, the battery charging chip, and the actual battery. Now they all speak on this line, SM bus SMC 5 G3 SEL. So right in the SMC tab over here where it says U4900 in the upper right corner, SM bus SMC5 _G3 SEL and SM bus SMC5 G3 SDA. So what is a pull-up resistor and what does a pull-up resistor do? And how is there a data line created here where these things can talk? Well, you have the SMC, the battery charger, and the battery. And you have these two lines, and these two lines are attached between these three chips by these resistors over here. Now, here's what this resistor does. This resistor takes 3.42 volts, and through 2 kilo ohms, puts 3.42 volts over here. Now, the way these chips work is they take that 3.42 volts, and they lower it. So every now and then, one of those chips is going to short that actual rail to ground. And through shorting it to ground, it's going to make these pulses, and these pulses create communication. Think of it like Morse code. Now, the problem here, if you didn't have the resistors, is you wouldn't be able to create a separate line. So on the other side of that resistor, on the other side of the resistor, which is just the basic PP3V42 line, that's 3.42 volts that's not going to be affected by anything happening. But on the other side of that 2 kilo ohm resistor, on the other side of that resistor, that's where all of this shorting to ground can occur without affecting the main power rail of the machine. So what you do with these is you create these separate power lines. That 2 kilo ohms of resistance in that resistor is going to keep everything that happens on the signal side of the resistor from affecting the voltage side of the transistor, the power line side of it. And the easiest way to get this across to you would be to actually show you what it looks like on an oscilloscope. So that's a 3.42 volt line of the system, right? Now I'm going to show you on the oscilloscope what this looks like, and unfortunately my oscilloscope does not have an HDMI output or a screen capture that I know how to use very easily, so I'm just going to be using the old ghetto way of zooming in with the camcorder. So let me just zoom in with the camcorder here, and now you can see the oscilloscope. So now let's get the probe over here. Now I attach the charger, and let's go on one of these lines. So now here's what the 3.42 volt side of the resistor looks like. This is the 3.42 volt power line. It's a standard 3.42 volts, or in this case here 3.6, because either my machine or my oscilloscope are running off spec. Good luck expecting anything to work around here the way it's supposed to. It will never ever happen. So let's just, now I'm setting this to 1 volt over here. Here we go. So every single one of those lines you see is 1 volt. So that's 3.46 volts that I got since I just set this thing up properly. When you have it set for each line to be 10 volts, it's not as accurate as when you have each line set to 1 volt. So that's 3.42 volts. That's the system voltage. Now on the other side of this resistor, that's where the line that attaches the battery to the SMC to the battery charger chip is. And let's see what that looks like. When we look at that side, it's going to look a lot different. See that? See that over there? Now I'm going to try to make it so you can see a little bit more. Here we go. See those lines? So you have 3.42 volts, but then every now and then what the chip is doing is it's actually shorting that line to ground in order to make these pulses. And that's how the chip communicates. So the chip is doing that, and then the SMC or the battery charger or the battery will be able to read what's going on. Don't ask me what the fuck any of this means, because I have no idea what that means. Like what those pulses mean, what the distance between them means. That is all code to me, and that is something that unless you are an Apple engineer, you will never understand, because none of this is documented. But the basic point of this is this, that this is what a healthy communication looks like. You have 3.42 volts at the top of the line, so it says VTOP in the lower left corner is 3.46, and then you have it going from 3.46 to 0 volts all the way at the bottom, and it's doing it in these little intervals. And again, you can create as many data lines as you want from one power source. It's very simple to do. You just take a resistor and you put it between a power line, and then you put it between that power line and what you want to be your data line. So again, on one side of the resistor, you're going to have the 3.42 volts, and you can create a data line with anything. It doesn't have to be 3.4. You can use 4, 5, 6, 10, 20, 80, whatever it is you want if you're making your own circuit. And on the other side of it, you're going to have the chip shorting it to ground every now and then to create these little pulses. And the length of the pulse and how far down it goes and all of that control pretty much is how you create this communication that's going on here. Now, let's do that with the other one, so you can see what it looks like. So that's a data line. So what a pull-up resistor does is it allows you to create a data line between different components that use that method of communication. So let's go back to where you can see me and where I can talk. Now, a common problem is going to be that something is shorting your data line to ground. And now there are many different data lines with the SMC in this machine. The battery talks to the battery charger, which talks to the SMC. You have sensors, so if your machine is running really, really slow, or your fan is on high all the time, you could have a sensor issue in your data line where one of the data lines is being pulled down by something. And in this instance, let's see where this thing goes. So I knew that something was wrong with the data line going to the battery, which is why I looked for SM Bus BAT SDA and SM Bus BAT SCL. So you have the battery, you have the U7000 battery charger chip, which creates PP Bus G3 hot, which I've talked about in other videos, and you have the SMC. Now, one of these three things was probably not working the way it was supposed to. I tried a new battery, and I still had an X on my battery. I checked R5280 and R5281, because if one of these resistors over here is blown, if one of those resistors is not there, you will have no data line. These chips do not actually create data. What they do is they simply take a line that already exists, and by shorting it to ground, that creates data. But without 3.42 volts there for this to short to ground, there's no data line. It's just going to be a constant 0 volts. Now, I checked on one of these resistors, and I had standard communication, and I checked on the other one, and it was 0 volts all the time. 0 volts all the time means that it's being shorted to ground. The resistor itself was still good. So what I noticed is that somewhere along this board, something was shorting that to ground. So it's either the battery, it's the battery charger, or the SMC. Or it could be this little battery indicator, even though it's not listed on here because sometimes these schematics just don't do what they're supposed to. That is actually one of the things that it talks to. So let's go over to the board view so I can show you what I mean. I'm going to go over to the board view. I'm going to hit the N key, which allows me to look up everywhere something shows up on the board. And of course, it's going to take me all out of where I was because this software sucks. So here we go. So that's the pull-up resistor. R5280, and you can't see my mouse, so I can't really narrate well. Then in the upper left corner, you have the battery indicator. It goes to the battery indicator. Obviously, the battery indicator, in order to know what the battery is doing, should be attached to the data line that's going to the battery. You have it going to the battery charger chip, the U7000, a little bit lower than that, and then below and to the right, you have it going to the third upper right ball on the SMC, which is U4900. So there are 4 possibilities as to why this is not working. The battery is bad, there's something wrong with the battery indicator, or the connector for the battery indicator could have some crap in it. There's something wrong with our U7000, or there's a short somewhere around the U7000 area, or it's the SMC. So to find the short, I decided to inject 3 volts into that line. I figured if I inject 3 volts into that line, whatever is pulling it to ground is going to get very, very hot. And I was dead wrong, because the short, while being a short, was not enough of a short to actually pull more than 0.1 amps. Good luck feeling a short when it's 3 volts at 0.1 amps. Nothing's going to get hot. So I decided, okay, I'm going to do this the hard way. I removed the battery indicator without removing the connector. Still same thing. I removed U7000 because it was next on my list, and the short went away completely. Thank God it went away completely, because if it didn't go away completely when I removed U7000, that would have meant that the SMC was bad, and the SMC is a chip that you replace by removing a bunch of balls that are like 0.3 or 0.25 millimeters and putting them back on. not something that you want to be doing at 1 in the morning. So I replaced U7000, and then instead of seeing a question mark on my battery, and instead of seeing an X on my battery, the battery actually worked. And one thing you'll be able to see with this computer, even after I unplug the charger, it's able to stay on, and it's going to work. I don't want to give away the wallpaper because then they'll know that I use their computer for a video, and you'll probably do creepy crap like stalk them, because I know that's what some of the people on YouTube like to do. But, let's see. Fuck it, I'll cover the desktop. As you can see, it works. It's on, and all is well. So this had an X through it before, and it was at 60% battery when I initially started it, and it's now at 75%, which means that I've done my job. So that's what I did to figure out why the battery had an X, and that's the troubleshooting process I went through to go from having a battery that was an X to a battery that actually shows up with information. Now to go over some other common issues, which are that the battery does not charge, it does not run off the battery, or it sees the charger but it won't actually run off of the charger. Now those are often current sensing issues. So let's go over what current sensing is over here. Again, I know that I haven't done the best job of describing how a data line works, but the basic idea of it is this. You take 3.42 volts and you create a flat 3.42 volts. And then any one of these components that would like to communicate with one another will simply take that 3.42 volts and decide, I'm going to short it to ground in short intervals in order to create those square-looking things that you saw. So every time it would short it to ground, for certain intervals, and the amount of pulses that you get from those random shorts to ground, the way it draws that little square looking thing is what decides what data gets sent. Do I know what the pulses mean? No clue. Do I know what any of those pulses mean, what the code is? No. And that is for people who are much smarter than me, who had a much better college experience than I did. But all you need to do is see that there's pulses there, compare to another board that works, get an idea if it's close, and you'll know. Again, if you see that the pulses are only going up to a maximum of 2.6 when the data line is being created from a 3.4 volt power line, you know, if this is supposed to be 3.4 volt power line that this is being created from, but it never goes higher than 2.6, is something pulling the line down. I have had that happen before. I had a webcam connector that looked perfect that was pulling a sensor line down to 2.6, and as soon as I removed the damn webcam connector, I was up to 3.4 and nothing was running slow anymore. So these are all things to think about. But now let's move on to current sensing. Let's move on to how this stuff works. Because this is so there are two different types of current sensing here. There's current sensing for the battery, and there's current sensing for the charger. Now, the chip by itself cannot really tell how much current or amperage the computer is using. It knows I'm operating at 8 volts, I'm operating at 12 volts, I'm operating at 18 volts, but it doesn't actually know how much current, how much power it's using. Ohm's law is going to allow you to figure out how much power you're actually using. And if you don't know what Ohm's law is, look it up in another tab, look up what voltage is, look up what current is, look up what resistance is, and look up how you can use those things to figure out how many watts something is using. So when somebody says this is using 100 watts or 200 watts or 1,000 watts of electricity, here's the problem with these systems. They use a standard voltage on the charger. So the charger puts out a standard 17 or 18 volts. Most laptop chargers put out a standard 17 or 18 volts. But how many watts are you actually using out of that? How much actual power are you using? That's something that these systems cannot detect. It can detect how much voltage is present in an area, but it cannot tell how much power is actually being used without being somewhere in the circuit. So current is sensed through a resistor. So right over here you'll see it says critical R7020. So the U7000, which is the chip that controls the charger and creates the main 12 volt rail for the machine, it can see that there's 18 volts over here. But what the thing cannot see is how much power the system is actually using. It needs to know how much power the system is using. Let's say it senses that the system is using 8 amps, and the charger itself is pretty much made to deliver 4 or 5. That little charger, the little MagSafe that you have is going to blow up into bits and pieces. And in order to protect that from happening, you have a current sensing circuit. So you have a current sensing circuit for the charger, which is right over here by R7020, and you have a current sensing circuit for the battery, which is right here by R7050. Now here's how that works. This chip can only sense voltage. It cannot sense how much power is being used since it is not inside the actual circuit. In order to know what's going on over here on R7020 between the top and the bottom, in order to know what's going on over here, And this is the area of interest because you get 12 volts for the system over here. The 12 volt rail is what the entire system runs off of. That is created by these two transistors, and these two transistors come from right over here where you have R7020. So you have R7020 going to Q7030 and Q7035, getting smoothed by L7030, and going through the fuse F7040. So going back over here, R7020 is the point of interest. This is where you're going to be able to figure out where 99% of the power the computer is using is actually being used for. So you have a resistor on the top of this small resistor, and then you have a resistor on the bottom of this small resistor. Now, what the ISL6259, this chip called the U7000 over here, is going to do, it's going to read the voltage on top of this very small resistor and the voltage on the bottom of this very small resistor. So R7020 is a 0.02 ohm resistor. That is a very, very small, very, very negligible amount of resistance. It's not going to cause a lot of extra load on the charger. It's not going to screw up the system at all. But it will create a very, very, very small difference in voltage. Through this 0.02 ohm resistor, which is barely even a resistor, there will be a very, 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 very small voltage drop. And that voltage drop is actually going to be dependent on how much power the system is using. So, knowing that there is a constant here, knowing that the voltage drop across R7020 is going to be constant, it's going to be different based on how much power the system is using, the U7000 can actually figure out current use, amperage that's actually going through the system based on the voltage difference between the top and the bottom of R7020. So from the top of R7020, you have a 10 ohm resistor going to U7000, and on the bottom of R7020, you have a 10 ohm resistor over here that's going to U7000. And it's labeled Charger CSI-RP and Charger CSI-RN. Now, here's what happens when it doesn't want to work off the charger a lot of the times. One of those 10 ohm resistors will be blown, will be destroyed. So one of the resistors will be 10 ohm, and one of those resistors will be something silly like 500 ohms or 1,000,000 ohms or infinite resistance and blown. And what happens when that happens is that it will sense a huge difference in voltage between the top and the bottom. Now what happens here is if it senses a huge difference, it's going to think that the computer is using millions of amps. The U7000 is going to say, okay, it's not using 2 or 4 amps, it's using 1,000 amps. And obviously the little MacBook can't use 1,000 amps, but if it thinks it's using 1,000 amps, it's going to say, fuck you charger, turn off. So I've had cases where the computer will actually charge when it's closed and it's off, but it won't charge when you turn it on. Because the difference in power usage when you turn it on would actually be enough to trip this broken current sensing circuit into saying, no, we're not supplying power anymore, and you would get battery as not charging. And the same would happen off the battery end. There are a lot of times where it says 58%. It can actually see how much power the battery has. You can read the cycle count. You can read all the information about the battery. You can read the cycle count. You can read the age of it and all that good stuff and how much power is left, but it won't run off of it. You'll take the charger off and the thing will just turn off. And the same is true here. So on this side of the system, you have R7050, and you have the exact same shit happening. So you have to and from battery, you're going to have your 12 volts, and you have a 0.01 ohm resistor here. And what that 0.01 ohm resistor is going to do, again, there's going to be a very, 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 very small negligible voltage drop across it. But that's going to be read by the U7000. Before R7050, you have R7052, which is a 0 ohm resistor leading the U7000. And after R7050, you have a 2.2 ohm resistor that leads to U7000. So U7000, again, this chip, since it's not actually inside the circuit, U7000 is controlling transistors that create the 12 volt rail for the machine. But U7000 is not actually inside that 12 volt rail. It's not going to know what's happening. But what it does is it measures the voltage drop across a constant in the circuit, which is that resistor. That 0.01 ohm resistor is always going to be doing pretty much what it's doing in that circuit. That 0.01 ohm resistor is always going to be creating a voltage drop, and that voltage drop is always going to be dependent on the amount of amperage the system is using. What the U7000 is doing is it's reading a constant within the circuit to figure out how much amperage it's using. So it's using a constant, which is 2 voltages that are based on the current the system is using to calculate the current that the system is using. And I'm sorry if I'm not that great at explaining this. I'm not much of a college professor. In fact, I really wasn't that much great of a college student, or an electronics student for that matter. Honestly, I know enough to fix this stuff and get paid for it, but I'm I am not a professor. If you want a professor, by all means go to college, where it will take you 4 to 6 to 8 years to learn the practical application of this so that you can actually make money. I'm just kind of skipping ahead to the part where you get to make money and have fun. So, long story short, you have a resistor in the circuit that's actually in line with the voltage rail that you'd like to measure current usage on. You measure the current, you measure the voltage at the top of that resistor, and you measure the voltage at the other side of that resistor. And what those two voltages are get calculated by U7000, and based on whatever values they programmed or measured in there or figured out, it pretty much tells the system this is how much amperage it's using. If it's using too much amperage, it turns it off. And if any one of those resistors or any of the traces to these resistors, which are, by the way, in high voltage, so it's close to the battery, it's close to the source of the charger, so those are going to be spots where if water hits there, you're going to see big explosions and nastiness on the board. Those are spots that you should look at, and those are spots that will usually be screwed up if your battery or your charger's not working. So, point is, this is not simple. This is not just, oh, there's a fuse that goes to the battery. People will always ask, why don't they just design it simple? Why can't there just be a fuse on the charger and a fuse on the battery? That would make this simple. There already are fuses there. They never blow. They only blow if lightning hits it. There is a lot more to the system than just having a fuse. Don't you actually want your system to turn off if something happens instead of blowing up the charger? That's what the high side current sensing is for by the charger. Don't you want the system to turn off instead of the battery blowing up and melting your genitals? That's what R7050 and R7051 and 52 are there for, to current sense in the battery. If it's drawing too much current from the battery, it's going to turn itself off before it melts your genitals. Don't you want to know how much power you have left in your battery? Don't you want to know if you're at 1% or 99%? That's why you have a system management controller that speaks with the battery via a data line that is controlled by pull-up resistors. You need these functions. Don't get pissed off that this is a complicated system, because at the same time that you're getting pissed off that this is a complicated system, you're going to be pissed off when your charger's blowing up, your genitals are getting melted, and it turns off right in the middle of an important Word document that you haven't saved because you didn't know how much battery you have left. When water gets spilled on this, any one of these complex parts of the machine can get turned to shit, and you need to understand exactly how they work if you want to repair them. You need to understand exactly how they work if you want to make money repairing them. It's not going to be something as simple as a fuse. You are going to have to turn your brain on. You are going to have to do some Googling. Hopefully, even if you understand none of what I've talked about in this video, even if I've done a terrible, terrible job of explaining it to the point where you have no idea what I'm talking about, hopefully, at the very least, I've given you things to Google so that you can learn for yourself. Even if my explanation sucks, and I know how that feels because I've went to look at some of these videos and I've went to look at some of these online descriptions where I'm like, how the hell does this guy expect that I'm going to understand what he's talking about? This makes no goddamn sense. He's the only one who knows it. At the very least, if you think that of me, you can Google what is a pull-up resistor. You can Google what is a data line created by a pull-up resistor. You can Google what is high-side current sensing. What is current sensing and how does this work? And then you can put it together in your brain and figure out why it is the machine isn't working. But what I want out of you is to stop asking these simple-ass questions and to stop assuming that it's a fuse. Stop assuming that everything is set up so simply, and stop just living in a world that is limited by your ignorance, that is limited by what you have not learned yet. Learn, Google, figure it out. Take the terms that I've given and run with them, and learn how to make some money for yourself off of things that other people would have called unfixable. When you go to Apple, when you go to the Apple store, when you look at the Apple service manual, when there is a problem with this part of the system, the service manual says replace MLB. MLB is a part that is often $400, $600, $700, $1,200. R7020, R7021, R7022, these cost 17 cents. The difference between 17 cents and $1,200 is nothing other than the ability to use your brain, which is something that the people at the Genius Bar have neither the time nor the inclination to do, but hopefully you do. And again, while you do have to learn some concepts, while you will have to Google, while you will have to apply some knowledge to learn this stuff, it's not going to be that hard. I assure you there are hundreds of people out there that will attest to the fact that they don't think that I have a working brain. There are a lot lot of people out there that think I'm pretty damn dumb. And if I can figure this out to the point where I can collect $325 plus tax for fixing this type of problem, then so can you. If you have any questions that are worthwhile, leave them in the comments and I will do my best to reply to them as I get a chance. Hopefully you learned something about troubleshooting battery and charging circuit issues on a MacBook Pro unibody, and have a good day.